Let's talk about some of the work we've done over the last year to make the CSS highlight pseudo system faster in Chromium. Over the last couple of years, we've been implementing the new CSS highlight system in Chromium, and although we're almost ready to ship, there's been some interesting challenges along the way, particularly around performance. The highlight system is based on the old selection pseudo, but it's a lot more powerful. And the consequence of this is that there's over a decade of existing content that must not get slower. Two important examples of this are universal rules, which apply to the highlights of all elements, and the default styles for spelling and grammar errors with the squiggly lines. Some of this new functionality requires us to do work that literally wasn't being done before, so our core problem is to figure out how to keep the fast things fast and the slow things possible. Over time, though, we found that in many cases, the design of the highlight system allows us to perform better than we were able to perform before, which has often been a welcome surprise to us. If there's only one thing you take away from this talk, it's that content that only uses universal highlight rules uses less memory under highlight inheritance, and user selection latency improves as well, at the expense of slightly slower initial style resolution. And thanks to some of our optimizations, most selections and spelling and grammar errors are not any slower under the new highlight overlay painter. In fact, we've even been able to optimize some lower hanging fruit that outweighed the slowness of highlight overlay painting entirely, but more on that later. So in this talk, we'll start with a recap of how the highlight system works, then take a look at some of the challenges we found with highlight inheritance. Then we'll look at the special behavior that highlights have when you set color to current color, which interacts with both style and paint. And finally, we'll look at the optimizations we've done around highlight painting. To recap, the highlight pseudos extend the non-standard but widely supported selection pseudo element. We have the ability to style selections, linked text fragments, spelling and grammar errors, and author-defined custom highlights. We only allow a small set of like 7 or 8 properties that don't affect layout because it would be a bad user experience and pretty slow if selecting some text could change things like the font size. Each of these highlights creates an overlay over the original content. Highlight styles now inherit from each other. So in this example, we have a body containing a P and an aside, and we've said that the body selection is yellow on black, and the aside selection is on dark red instead. Highlight inheritance means that the aside selection will be yellow as well, inheriting its color from the body selection, and the sub selection will also be yellow on dark red. How the highlights used to work in most browsers was like other pseudos, where the styles inherit only from the originating element. So in the same example, the P and sub elements would reset to the default selection colors, not yellow and dark red. You can work around this by also selecting the descendants in each rule, but highlight inheritance makes this awkward workaround unnecessary. Highlight overlays can each have their own backgrounds, line decorations, and shadows. So in this example, we have the text quick brown fox, and the words quick and brown have a strike through already. The word quick is misspelled, so we add a squiggly decoration. We have target text on brown, which adds its own background, so we need to lift the text up into that layer, so it paints on top of the background. And the user has selected the letters K, C, B, and R, which also adds a background. And to ensure that the original decorations remain legible, we also recolor those decorations to the same foreground color as the topmost highlight. Now, onto style. There are 2 points in time that we calculate styles. The first is the style phase of the renderer, where we calculate styles for originating elements, and then for some pseudos, we calculate those as well, recursing down the tree and invalidating as needed. The second way is to calculate pseudo-styles lazily, caching them in the originating element. We use this lazy approach for situations like, for example, if the page calls getComputed_style on the before pseudo, but the before pseudo doesn't actually exist because it doesn't have the content property set. We also used to do this for highlight pseudos. This works well enough for pseudos that inherit from the originating element, because when the originating element styles change, the cache will get blown away anyway. But for highlight pseudos, we need proper invalidation down the tree now. And unless we re-implement all of this invalidation machinery, we're kind of stuck. So as a result, we needed to move highlight styles so they're calculated eagerly in the style phase. To understand how we've done highlight inheritance, it would help to understand how styles are resolved for ordinary elements. We start by shallow cloning the initial computed style, which basically contains the default styles that apply to any element. Then we copy all of the inherited properties from the parent style, but none of the non-inherited properties. Then we search our style sheets for rules matching the element. And importantly, in this step, we also encounter pseudo-element rules for that element. But if we get a pseudo rule, we'll just mark it down in the pseudo bits for that element and skip the rule. Finally, we sort the rules based on the cascade, and we apply the final set of properties to the computed style, overwriting any inherited or initial property values as needed. The shallow cloning here is because we actually break up the computed style object into field groups, which reduces the overhead of less commonly used properties by allowing us to copy on write and share parts of the style data that haven't changed. On the other hand, resolving highlight styles is easier in a way because all properties are inherited, even if they're not normally defined as inherited. So all we need to do is shallow clone the parent, search for matching rules for that pseudo element, then cascade and apply. The bad news out of all this is we may need to calculate highlight styles for every element, even if they don't directly contain any content that can be highlighted. So in this example on the right, we have a tree where only the P and the aside actually have text, and the user hasn't even selected the P yet. Under the old system, we would only need to calculate styles for aside selection at this point. But under the new system, we will also need the styles for HTML, head, and body, because the descendants might need to inherit styles from them. Another consequence of highlight inheritance is that we now resolve the styles up front, not when the content actually gets highlighted for the first time, like that P selection on the right. This might be a good thing or a bad thing, depending on how you look at it. But the good news is that because all properties are inherited, in highlight styles, we can actually inherit styles at zero cost in some situations. The key idea behind this is that we get to take a peek at the matching pseudo-element rules while calculating the originating styles. So we can use this knowledge to not even begin to resolve some highlight styles. The classic example of this is the pseudo bits, which tell us whether there were no matching rules for a given pseudo-element at all. But when there are some matching rules, we can also add information about those rules that allow us to skip resolution in other situations that are especially relevant to highlights. The most important style optimization here involves checking if there are any non-universal highlight rules matching a highlight at some point in the tree, because universal rules apply everywhere in the tree. So if you only match universal rules and your children also only match universal rules, then they will have the same styles, more or less, and they can almost always reuse your styles. On the other hand, if you matched some non-universal rules, then you need to calculate your styles normally, and so do your direct children, just in case there are universal rules that need to be mixed back in. But beyond those direct children, we can continue reusing styles in descendants again. This significantly reduces the amount of work we need to do for highlight inheritance, improving performance of both pages that use universal rules only and pages that use highlight inheritance properly. Unfortunately, this doesn't help for the root element because the root element has no parent whose highlight styles we can reuse. And this is kind of problematic because for the spelling and grammar highlights, we add some rules to the UA style sheet saying that by default, they add spelling and grammar decorations respectively. This slows down every recalc for the root element because we have 2 additional rules that we need to match and apply each time. But the thing about UA style sheet rules is that we know we won't change them for the lifetime of the page. So if we've computed the root highlight styles before and they only came from UA style sheet rules, and we still only match UA style sheet rules now, then we can just reuse the old root highlight styles. Now for the special behavior that highlights have when you set color to current color. Current color is a special color value that means the computed value of color. Now this would be kind of circular for the color property itself, so when you set color to current color, it instead means don't change the foreground color in this child or highlight or whatever. The way this is achieved normally is that we define it as equivalent to setting color to inherit. On the other hand, for highlights, it's a bit more complicated because we need to know what highlights are active underneath. This means that the result of color current color might not be resolvable until paint time. But wait, it gets worse. Computed style promises callers that they can ask for any color valued property at any time and always get a concrete color. And much of the style system and Blink in general expects that color current color is never actually stored in computed style, so that a computed style object can be completely self-contained. In theory, we need to make all these interfaces return an optional now, representing the case where the color is unknown until highlight painting. But this would complicate the whole engine with optional checks, and it would probably be pretty hard to do without perf regressions. So the solution we came up with is to keep track of whether color was set to current color, which again is something that was already being done for every other property, just not color itself. So we add flags for whether color and its internal visited counterpart was set to current color. And these flags don't affect non-highlight code because they can just ignore these flags. Then we also need to add an optional out parameter to several color-related interfaces in computed style. Things like visited dependent color, resolved color, color including fallback, and so on. And this also doesn't affect non-highlight code because they can just ignore the parameter. These two changes are enough to support the behavior of current color in highlight pseudos, but let's take a closer look at exactly how they do that. All of Blink's color interfaces ultimately call the styleColor_resolve function, which is where half the magic happens. The function continues to take a concrete current color and return either that or another concrete color value, and that's good enough for non-highlight usage. But now, the highlight code can also opt in to being told whether the value was actually current color, so it knows it needs to use its special highlight rules to resolve the color properly. The other half of the magic is in highlight painting utils, which is where we have previously kept things like the logic for paired defaults and resolving and caching highlight styles. We can add a new util that checks for forced colors and paired defaults, then tries to grab the visited dependent color, and if it's not current color, then we're done. It's as simple as that. But when we're told that it is current color, then we either need to recurse with the actual color property itself, or if we were already trying to resolve the color property, then we can return the next layer color based on the highlights that are active. As for paint, let's start with how the new overlay painting algorithms work. In order to paint highlight overlays, we need to know the painting order of those overlays, and we also need to know which parts of the text fragment have which highlights active. Getting the layers is pretty straightforward, but before we can compute the parts, we also need to figure out where all the highlights start and stop throughout the text fragment, which we'll call the edges. To compute the layers that are relevant to this text fragment, we basically go through all the highlighted ranges and push an entry for each unique highlight pseudo we see. So in this example, we have a selection, a target text highlight, and a spelling error. And we need to make sure that they're sorted in the highlight painting order, where selection goes last. To compute the edges, representing where the highlights start and end over the course of the text fragment, we need to take each highlighted range and push two entries, one saying where the highlight started and one saying where it ended. Then we sort these entries by the offset into the text fragment, then by which layer it was and whether it started or ended. So in the same example, we have a selection that goes from 3 to 8, a target text highlight that goes from 6 to 11, and a spelling error that goes from 0 to 5. And sorting it like this, we then have a list of edges saying that a spelling error starts at 0, a selection starts at 3, and so on. Once we have these edges, we can break the text into parts and determine which highlights are active in each part. We're going to walk through the text fragment using a set of flags to keep track of whether each layer is active. So from 0, the spelling error highlight starts, and from 0 to 3, spelling is the only highlight that's active. From 3, the selection highlight starts, and from 3 to 5, we have both a spelling error and a selection. At 5, the spelling error ends, so we're back to only having a selection. At 6, the target text starts, so we have a target text highlight and a selection. At 8, the selection ends, so we're back to only having a target text highlight. And at 11, the target text highlight ends as well. So we just have an edge here from 11 to 15, where it's just in the originating element style. One thing that complicates these calculations is that although the web platform's selection and custom highlight APIs are based on DOM ranges, which basically go from an offset into one node to another offset in another node, the text actually on the page can be different to what's in the DOM. This can happen for a bunch of reasons. The most common one is that white space is usually collapsed, but CSS can also generate an ellipsis or apply a text transform that changes the length of the text, and soft hyphens can generate an additional character for the visible hyphen. As a result, we sometimes need to convert between DOM offsets and what we call canonical text offsets. Another problem comes from trying to determine what highlights apply to a text fragment. So aside from the selection pseudo, we use the document marker controller to do this, which splits DOM ranges into buckets for each node, but ideally we only want to ask for the ranges that apply to our text fragment within the text node, which usually means like one line of text. This mismatch means that we need to clamp and sometimes discard ranges that apply only to other text fragments. Some of the main optimizations we've made so far in Paint have been in response to perf regressions in scenarios that are already pervasive on the web, including user selections and spelling and grammar errors. We want to add fast paths for these scenarios, allowing us to paint them more efficiently, either just naively like we used to, or by removing some of the overhead of the full overlay painting algorithms. In general, the underlying strategy here is to identify scenarios where only a single highlight pseudo is active, and see if some of them can be painted more efficiently. Because if more than one overlapping highlight is active, we almost always need the proper highlight overlay logic anyway. For selection, we have a fairly easy optimization that pretty much boils down to falling back on the old code, which was fairly well optimized and can even do some things that the other highlights haven't even implemented yet. The old code worked by painting the originating shadows, then the text and decorations that go before the selection, then the part that goes after the selection, and finally, painting the selection background and the selected text. But decorations are where this falls apart, because the originating decorations need to be combined and interleaved with any decorations that the selection adds in a particular way. And originating decorations also need to be recolored for legibility. As a result, we can only really use this fast path when there's a selection highlight without any originating decorations. The default styles for spelling and grammar errors is to add a squiggly line decoration without changing the text color. But CSS leaves the appearance of these decorations completely open to UA interpretation. So why not paint the whole text in a single pass, then just add some squiggly lines on top where there are spelling errors? Now, because the spec is so flexible about these decorations, we don't need to interleave them with the originating decorations, but we still might need to recolor them. So this fast path can be used if there are only spelling and grammar errors that only add spelling and grammar decorations without changing the text color or adding any other decorations or shadows. But we also need to check if the originating decorations match the highlight foreground color. Thankfully, most originating decorations are in the same color as the text, and we would expect most spelling and grammar errors to have the same foreground color as the text as well, so this requirement isn't too hard to meet. If you're like me, you're probably thinking, this seems kinda inefficient and complicated. Maybe we should rethink these algorithms, or at least make some significant optimizations to them. And there's certainly room for improvement. For example, we could rework the data structures in the document marker controller to allow us to efficiently query only the markers that touch a specific text fragment. Or maybe we could cache the layers, edges, and parts across paints. Or maybe we could add incremental updates for these data structures so we don't have to recompute the edges and parts from scratch over and over. Or maybe we could make repaints within a text fragment more incremental as well. And while those are all good ideas, it turns out that these new algorithms just don't matter that much in the grand scheme of things. We made a paint perf test simulating a user typing where each word of their input became a spelling error. This was an actual regression that we had to fix earlier this year, and it can happen pretty easily if a user pastes or types in an input field set to the wrong spell checker language. When we profiled this test, we found that the most expensive parts of the new highlight painter, by an order of magnitude, were not the new highlight overlay algorithms, but two other operations. One was converting DOM offsets to canonical text offsets, and the other was computing the rects for highlight background colors and decoration clipping. What surprised us even more was that this was true for the fast paths, which bypassed most of the overlay painting logic, and even for the old highlight painting code that didn't support overlays or decorations at all. For more details, you can grab a copy of these slides from the link at the top, check out the blog posts below, and as for whether the new highlight pseudos are fast enough to ship in Chromium, I'll leave you with this demo, which is made entirely out of custom highlights. You be the judge.
And we'll pull that down a little bit. Open the floor for questions for Dylan. Keep rolling, translation. I was so expecting this to turn into Never Gonna Give You Up. Yeah, I saw a question in chat if somebody wants to raise their hand and actually ask it.
I'm not sure if I'm coming through okay.
Yeah, you good?
How much work was the demo as compared to implementing the feature? The demo... the demo I mostly did in a night, but I dug up an older demo where I was trying to, use custom highlights as a canvas. And I guess in total, it took like 3 days of work. The feature, I've been working on this for almost 2 years now. So hopefully I can move on to something else next year.